Hello everybody. In this video we will discuss reaction of ester functional group. So what is an ester functional group? Ester functional group is when you have carbonyl and an oxygens right here. That's an ester functional group. So when you have COO. Okay, so what happened when we react ester with Grignard reagent, and I will have, so let's say we have an excess of these things. Okay, so when you see a questions like this where it's written as 1 and 2, that means both of the reactions were added one after another. Like it's not a crockpot reactions where you dump Grignard reagent and your acid H3O plus together. It's a one after another because you cannot have any acidic proton in your Grignard reagent. Otherwise, you will kill your Grignard reagent. It's just going to neutralize. Okay, so what would happen? So let's start over a few basics. So if you look at your compound CH3CO OCH3, we know that the carbon atom is slightly positive, delta positive, and oxygen is delta negative. So if carbon atom is positive right here, this is positive. So what would happen? Anything that is negative, so anything that is negative, so if you have a nucleophile with electron, that electron would go and attack, right? So who is our nucleophile in our equations? Well, our equations here, we are using Grignard reagent CH3MgBr, and we know that would react as if, so we have been using this Tactus shortcut, would react as if this is CH3 minus. So basically, this CH3 minus, carbon atom is more electronegative than magnesium, so it will get these two electrons and becomes negative. So it will react as if this is CH3 minus. Okay, so you can just simply attack the negative with positive. So we have negative here and attack. So as soon as you attack, what would happen? You're gonna have 5 bonds here, right? So you cannot have 5 bonds on carbon atom. So to maintain the octet, you will push one of the pi bond here. So we got 2 bonds here. So a pair of pi electron towards oxygens. Okay. So oxygen has 2 lone pair to begin with. So what is the product going to be here? So our product is going to be, well, not product, the intermediate, CH3CO minus OCH3, and we just added our Grignard reagent, CH3, whatever it is, okay? CH3. And the reason oxygen has 3 bonds, based on our shortcuts, remember when oxygen has 2 bonds, that's neutral, 3 bonds positive, 1 bond negative. The reason it's negative because it has extra electrons. It abstracted the pi electron from CO bond. Okay, so now this is very critical. So oxygens, so this here, this oxygen, not the oxygen, the carbon atom here is sp3 hybridized, but before it was sp2 hybridized. So here it was sp2, but here it is sp3 hybridized. So when something is sp3 hybridized, that's our tetrahedral intermediate, right? So you will create a tetrahedral intermediate. Okay, tetrahedral intermediate. The tetrahedral intermediate with O negative is unstable and it wants to go back to sp2 hybridized state by removing a group. Again, it's not going to be able to removing a group if possible. if possible. This idea is important. We have talked about this before. If possible. So I should highlight that, if possible. So what does this mean? So what I was trying to say here is, so it wants to go back by removing a group. I will explain why I have chosen this. So you will make CH3 CO. So now you're back to sp2 and CH3 plus CH3O minus CH3O minus. Okay, so this one here, the reason we removed this group here, because this group is a decent leaving group in comparison to the other one. So what if I would have leaving this one? If I would have left this one out, so the leaving group would have been CH3 minus. So CH3 minus is a bad leaving group. So this one here is a bad leaving group. So anything with the carbon, so you cannot kick out any R minus group because they are bad leaving groups. So how do we know? How do we figure out which one is a good leaving group? So you can compare this versus CH3O minus. So first thing that you want to find is their conjugate acid. So in this case, the conjugate acid is CH4. Here, conjugate acid is CH3OH. Then find their corresponding pKa values. pKa of the CH4 is the acidic proton right there is very high, 60. So it's very basic. It's almost very weakly acidic. And here it's roughly around 16s. Alcohol pKa is roughly around 16. So this one is more acidic and this one is less acidic. And if something is less acidic, the corresponding base would be more basic. So this one is more basic. So in simple term, this is highly basic. Very basic. So you're not gonna have ever a carbon group Cr minus. So you're never gonna have, so you will never have R minus or H minus cannot be kicked out. Cannot be kicked out. Okay, so you cannot remove either CH3 minus or hydride minus H minus from here. It has to be pKa much smaller. So in this case, we can do this. Okay, so let's go back. So what we have here is this CS3CO CS3. So this reaction won't stop here. So let me delete all this stuff here. That way we can go further from here. Okay, so the reaction won't stop here. What would happen is, so if you notice, it is still back to sp2 carbon atoms. So this is still sp2. And what happened? This here is still delta positive CO bond and this delta negative. In our previous video, we know what functional group is this one. This is a ketone, right? So ketone will again react with anything left over. So CH3 MgBr, it will react again because as soon as you make this, it's gonna react with whatever the next CH3 MgBr available. So that's why I said we have excess here, right? So we have excess here. So as soon as you make this molecule in your reaction, it will have a next set of reactions. And we know this would react as if CH3 minus, right? So the CH3 minus will go and attack on the carbonyl carbons because carbonyl carbon is positive. Delta, this is your delta positive. So you will react here, and you'll push the pi electron again towards oxygens, and then you make another tetrahedral intermediate, CS3 CO minus, and we know it has 6 lone pair, and then you're gonna have CH3, and then we're gonna have a second set of CH3 here. And at this point, can I remove any group? None of the group can be removed. None of the group can be removed because CH3 minus is going to be a bad leaving group because it's highly basic. Okay, so you cannot kick out any of the groups. So it's not going to happen, not going to happen, not going to happen. So this is where it's going to stop. And what's going to happen is the next step of the reaction. So all we're going to do is neutralize it. So just dump some acid. So that's the final step of the reactions. You're going to add some acid. That acid is basically neutralize the positive negative charge on oxygens. So this is where in questions you might see H plus, or you might sometimes people just write H3O plus. So either one, if you see in your questions, the basic principle is we are just neutralizing the negative charge on oxygens. CS3, COH. Okay, maybe I should color code just like I did. So we will make CS3COH. So you see we first added the pink oxygens, then added this brown oxygens. We first added the pink carbon atom, pink methyl group, then we added the brown methyl group. So when you react an ester with Grignard reagent, you make a tertiary alcohol, and just make sure the reaction happens twice. And what is the byproduct for this reactions? Don't forget CS3OH. So why CS3OH? So you notice we made CS3O minus in our previous step, right? So it's still hanging in there in your reaction. So it's still hanging in there, CS3O minus. So when you neutralize it, everything gets neutralized. So you can neutralize this O negative, you can neutralize this O negative as well. So you will make these two products. So these are your answers. There we go. Let's stop this video here.